Thanks all for listening. So I've got about 17, 20 slides or something, and I'm going to talk about CCS, but I'm talking about it in quite a different way to what Mark talked about it, which is why we're all having different points of view tonight, so that's good. And I guess it relates really a little bit to what Ashley was talking about. I've got a lot of sympathy with that. This is the old college in Edinburgh University, and for those of you who are not from Edinburgh and maybe not even from Scotland, on the northwest corner of that college is the place where carbon dioxide was first isolated in the world by Joseph Black. So I just thought I'd give you that free factoid around 1770. Edinburgh University is responsible for isolating carbon dioxide, but will not be responsible for any of the climate damage, I've no doubt. So moving on to what we're talking about, it's clear we all have to do something. So here's Siberia burning on the top left, here's bits of California burning, and there's Australia burning. And if it's not busy burning, then it's busy melting and raining. So in the middle at the bottom is the summer extent of Arctic ice with the yellow line as it used to be. In the 1970s and 80s, and this is the very much thinner summer ice at the present day. And as you probably know, people are starting to think about sending shipping through the Arctic, which is a really bad idea, because if you lose that reflectivity, the warming of the world heats up. And here's unprecedented flooding in my local town in Fife. Hasn't happened before like that. So we're living in unprecedented times, no doubt, really about climate change. And that leads the proposition to net zero. So there's a load of writing on this, which you don't need to read. But what it said is, either by accident or design, Theresa May committed the UK to move to net zero by 2050. And that turned out to be the best thing she ever did in her administration, probably, because it means that instead of going down to 80% of carbon emissions, we now go down to 100%. Because what had happened with 80% of emissions was that everybody thought they were going to be in the last 20%, so nobody did anything. Whereas now everybody is in the 100%, so everybody has to do something. The UK, in terms of emissions per year of CO2, the UK has been extremely successful at reducing emissions since 1990. So it's got about halfway towards a zero goal. But it's done that not by capturing CO2, but it's done that by getting rid of coal. So it's pretty much exactly in the same way that Mark was talking about. If you take coal as your baseline for electricity and power generation and power in the economy, it has all sorts of upstream emissions, it has all sorts of downstream emissions, and you get a little bit of electricity in between. So the UK priced coal out of the market by putting a £20 a tonne carbon tax on in about 2017, and that quietly stopped any companies rebuilding their coal-fueled power plant. And the last one will close down in about 2 years' time. The UK is on a pathway towards net zero, which is where the emissions balance the negative carbon, the carbon recaptured. The UK is trying to get there by 2050. China, interestingly, last autumn declared that it would get there in slightly different language by 2060. So China emits about a third of the world's CO2 at the moment. So that's also the best thing which has happened in the past year or two, that China's made that pledge. Though how they're going to do it, we don't know. But what I'll also draw your attention to is on this graph is the rest of the world during this UK emissions decrease, the rest of the world has not changed its emissions per person significantly. So what that means is that all the renewables built all around the world, all that wind, offshore wind and solar has had no net effect on changing the carbon emissions. So we've managed to dig up just as much carbon and use it and expand our economies, and the renewable electricity has really supported the expansion of the economy. So we actually have to do something smarter than just closing coal plants and smarter than just building a bit more, a load more renewables. So what are we going to do? Well, obviously I'm going to propose carbon capture and storage. So we have large legacy coal plants, which are now a large legacy biomass plant. Instead of sending coal-powered CO2 into the atmosphere, Drax is sending tree-powered carbon dioxide into the atmosphere at the moment. If carbon capture can be fitted onto that, that is worthwhile. But if it can't, then it's not and has to close. And we also have large amounts of industry in Britain, which is processing petrochemicals, but also making stuff like plastic and pharmaceuticals and paint and other things that we use routinely. So what we have to do, and we also use lots and lots of gas, methane gas in our heating, cooking and transport. And what we have to do with all those is find a way of bottling those up. And I have now, there it is, bottling those up. So we want to be able to get rid of those fossil fuels, but it's going to take a long time to change that economy. So you could change the economy overnight, but it would be very cold and you wouldn't have very much to eat. So that's unacceptable to most voters. So what we're trying to do here is find a way of using the fossil fuels for another 20, 30 or 40 years whilst we transition to renewables, greater efficiency and smarter ways of generating electricity and chemical energy. So we need to find a way of using the fossil fuel without the emissions, which is what the carbon capture and storage is all about. That involves handling large amounts of CO2. And as we know, since the 1970s, early 1970s, CO2 has been extracted from natural sources in the United States, put underground to dry clean oil out of rock. It dissolves that oil out of the rock and brings the oil plus CO2 to the surface. In a commercial operation, that CO2 is practically always, in fact, to my knowledge, always recycled, because that costs money and the operators don't want to spend another few tens of dollars per ton of CO2. Anyway, so that's an established process. We know how to handle CO2, know how to drill wells, etc., etc. As Ashley talked about, here's the original project in the North Sea, the Sleipner project, which is in the center of the North Sea. That's doing a similar type of thing in the sense that it's bringing oil plus carbon dioxide up from downstairs, stripping out the carbon dioxide in a module, a platform offshore, and injecting that carbon dioxide into a saline formation. And that that's to reduce the emissions offshore. So this is a net emissions reduction of that processing, plus the 8 or 10% of carbon dioxide which would have been emitted into the atmosphere had the Norwegians not had enough brain to put a $50 per ton carbon tax on all emissions offshore. And that has driven this behavior change to make Sleipner capture and store CO2, which would have been emitted from the mixture with its oil, and also to capture and store the Snøhvit emissions, which Ashley talked about. So these have operated safely and securely since 1996 at 1 ton, 1 million tons a year, 0.7 million tons a year. But a single borehole, it's easy to demonstrate with reservoir engineering, a single borehole can put away 4 million tons a year if you want it to, if you've configured it right. So we get full exam marks in May, first class honours degree for doing that. And I want to emphasize then that what we're talking about here is CO2 storage, because I'm not assuming people know very much, is that CO2 storage is putting this into layers of rock which are kilometers underneath the surface. Many cartoon sketches show this as if it was just underneath the car park outside the library building, but it's not. It's 3-4 kilometers down, and the carbon dioxide goes into the pore space of the rock, displaces the saline water, and needs to be mechanically sealed underneath an impermeable mudstone for at least 10,000 years. And to most people, 10,000 years is a long time, but to me as a geologist, 10,000 years is barely worth thinking about. It's such a small amount of time. But we know we can do this because we can find plenty of places in the North Sea, in Italy, in Colorado, in Arizona, in Germany, in Iceland, where there's natural CO2 stores which have lasted orders of magnitude longer than that. And the CO2 then gradually dissolves in the pore water underground, giving you saline, fizzy water. And the sandstones we want to put that in are massive sandstones. Again, to get the scale right, that's why the UK is planning to do this offshore. Here's a sandstone exposed in North America, which is basically 100 meters in thickness and the size of the city of Edinburgh. Okay, that's the size of footprint of storage site you need to have. So in North American terms, this again is piffling small, but in British terms, that's large enough that we have to put these offshore. And we've got multiple layers of sandstones offshore. We've got maybe 10 different layers of sandstone offshore, which we can use. Globally, that's been analyzed at a relatively superficial level. Here's a map showing you the amount of billions of tons of gigatons of storage per year offshore and onshore in the United States, in Canada, Brazil, Europe, different parts of Africa, China, Australia. And the answer you're wanting me to say is there's about 11,000 billion tons of storage in prospect, enough for 200 years of emissions. So if this got developed, and if we wanted to go for this in a big way, then it is a useful attribute which would try and get us through the next 50 years while we decarbonize and adjust into using zero carbon. There are lots of CCUS projects tested around the world. Most of these are pilot tests. And at the moment, there's about 40 million tons a year being captured globally by commercial tests, capturing from clean gas, from stripping carbon dioxide out of gas, capturing from now one power station. There's one in Boundary Dam and coal plant up there, and capturing from multiple industrial facilities worldwide. And all of that, I assert, is actually carbon dioxide, which would have gone into the atmosphere. And but a lot of that goes to a different market. So the capture step is successful. That's proven, that can operate, and that can improve up to 99% on site. I'm not counting the upstream emissions, which Mark talked about. We can do that in questions. But let's separate the successful operation of the technology for capture from the unsuccessful creation of a market, because a lot of this goes for CO2 enhanced oil recovery, and you put 30 million tons into the ground and you bring out another 25 to 35 million tons of carbon with the extra oil. So as a climate mitigation, doing enhanced oil recovery has not been correctly configured. It is possible to do climate mitigation with EOR, but not in the present circumstance. And as some of us might know, then one of these large CCS projects is proposed for Aberdeen, the Acorn project running from St Fergus, where lots of oil and gas comes onshore, turn those pipes round effectively to reuse those pipes, capture CO2 here at St Fergus, capture CO2 around Aberdeen, capture CO2 in the central belt of Scotland, and pipeline that up to St Fergus, send that CO2 offshore. So we're reusing lots of existing equipment, so there's no extra carbon cost in the infrastructure for that. So it's actually a way of saving 70% on the price, and that's partly because of the expression of saving on new infrastructure. So again, that's a type of conversation we can have. And Ashley, I quite agree with, saying that we should be thinking very carefully now about how to reuse our infrastructure, reuse the existing oil fields, reuse the existing equipment, reuse the knowledge and skills we've got. And the oil industry is the way out of this problem rather than the way into the problem. But the government has to bite the bullet and make different rules to what the rules are at the moment. But we're now seeing this happen. Some of you might have noticed there was a big legal case won against Shell in The Hague a week ago, and that, I think, makes Shell clean up their emissions by 2030 at twice the rate they were planning. So this is the start of a set of dominoes, I think. And by 2050, it's quite possible to envisage a CO2 storage industry in the North Sea, replacing the present size of the oil industry in the North Sea. These green lines representing new pipelines, bringing CO2 from various parts of Scotland and the rest of the English peninsula up into, and from Europe, into be stored in the Norwegian, UK, Danish, and Netherlands parts of the North Sea. So on the Norwegian side, similar mirror image project bringing energy from waste in the Oslo city region, capturing CO2 at a cement plant. Again, industrial emissions. You can build as much wind power as you want and you're never going to decarbonize cement. That has to be done physically by capturing that processed CO2 and sending this CO2 offshore to store here. And here's the market for all the companies, businesses, and industries all around the coastal parts of Europe in the top right of the picture, who are wanting to buy into that carbon storage option. These are people with fertilizer, cement, steel, energy from waste, biomass plants, who all want to store CO2 to become carbon neutral or even carbon negative. Why do we need CO2 storage? Why don't we just electrify everything? Well, because if we look at our energy consumption, then electricity on the left-hand circle, electricity is about a quarter of our energy consumption. Out of that electricity here, this circle on the right, out of that electricity, something like a third to a half, depending which day of the week it is produced by burning gas. So hidden within that electricity is indeed about 50% renewable, but they're still entirely dependent on fossil fuel. Okay, so we've made progress, but we're nowhere near good enough yet. And then in your house and my house right now, we're busy burning gas for heating and warm water. We're busy burning gas in lots of other industrial operations, and all of the vehicles on the road and the airplanes and the trains are busy using oil. So we've got a huge journey to go to decarbonize all this, and it's going to take a long time. So yes, you can electrify stuff. Yes, you can put hydrogen fuel cells in equipment and transport. Yes, you can fuel switch from gas into electricity with some things, but not easily with everything, and not fast. And so CCS has not just a power application, but it has an application to decrease end pipe emissions from gas fuel power plant, from oil refineries, from cement works, from steel works, partially. We'll talk, you can turn some of that into hydrogen by splitting methane. We're on a journey to make more and more methane with electrolysis, but we need to quadruple the number of wind power and PV panels so until we can get enough hydrogen. We can switch industry onto hydrogen or with new decarbonized direct reaction processes, for example. And importantly, we can use direct air capture to capture the bits which these industries, these end pipes did not capture. So the fixed price, the fixed global price of direct air capture powered by wind, I think, or solar, will actually be a game changer globally. And so there's a project in Scotland now which aims to start direct air capture powered by wind. And what we have to do is go down in our carbon emissions. I think Ashley showed a graph a bit like this. So we've had a slow historical increase, 3% per year, 3% per year of cumulative CO2 increase since the Industrial Revolution, but we've left it too late, and we now need to decrease at 8 or 9% every year until 2050. So that's probably impossible, but we'll have a go. And when we get to net zero, that means when we're still emitting carbon dioxide, we're still continuing to emit because it's a slow decrease and a slow change of industry and machinery and equipment and cars and factories. We'll still be emitting. We then need that carbon negative to balance that net zero. When the net zero point is when emissions are balanced by recaptured CO2, which can be from trees with biomass, but I think we're going to be much more successful with direct air capture because we basically can't forest enough of the UK fast enough. So we need to be efficient, we need renewables, and we need to remove carbon. And just to show you the difficult, I've big fan of forest, but let's be realistic about it, that each of us in Europe needs 3 football pitches of forest throughout our entire life to carry on working as a carbon sink if we're to balance emissions with forest. And that's quite risky. It can work, but we need to, it's clear that forest fires are increasing and will continue to increase. And if we do plant that forest, that carbon has to be captured. What do you do with the end of the forest? At the end of the forest, that carbon has to be captured and stored by using biomass CCS of some form or another, but probably much more locally than Drax is doing it at the moment. Other advantages of carbon capture and storage is that it lasts for a very long time. Here's a 3-dimensional graphic of the Sleipner project in the North Sea I talked about. We can see the carbon dioxide underground by shooting oil company seismic. Again, this is run by an oil company, uses existing technology, and you can image there 0.001% of the injected CO2. It's very high quality reliability. You cannot measure in a forest the amount of carbon stored to that amount of accuracy or precision. And you can't measure that accuracy and precision of carbon stored in soil with that accuracy and precision, and nor with that longevity. This carbon stored in geological storage will last for 20, 30, 50 million years, very safe and secure. Contentious slide, old carbon capture plants with coal-fueled power plants with carbon capture and storage designed, and then the red dots fitted. This will probably be the one Mark was talking about. Clearly, there is a trajectory for the price to decrease. The price of capturing carbon will always be more than not capturing carbon. But I quite agree that, as Mark was talking about, a full life cycle analysis of what carbon actually costs to store and capture is essential. And it's essential that the capture costs are fully integrated with that capture and storage life cycle analysis. So the price in money is one thing, but the price in carbon is also an important factor to happen. And the other thing for us in the UK is that most of our energy is not supplied by electricity through the year. You've probably seen this slide before. Here, the red is the electricity every day throughout the year. You can see we use a bit less electricity in the summer, like now, because it's warm. But most academics and university people and governments spend their entire life looking at these little twiddles in the electricity consumption curve. Whereas actually the amount of energy we use from gas, from methane gas, is very low at the moment because I'm just using hot water in my house. But in the winter, I use what's colloquially called shed loads of energy in using gas for heating my house, and also in so I use a lot. So I use 6 times more energy in the winter. I need 6 electricity systems in the winter to balance the peak demand. And I also need 3 electricity systems every day to balance that incredible increase in demand when everybody turns their central heating on at 6 o'clock in the morning. So that's impossible to do with our existing electricity system. You can only do that either by huge amounts of storage. And we're about 1,000 to 10,000 times off at the moment with batteries for the national grid. The amount of pumped storage water will power about one of these part way up one of these spikes. So, you know, we're a long way off. So the solution to this, where I propose, and we've got a lot of support for this in the UK, as you probably know, is we have to go for chemical energy. So we replace the methane with hydrogen, and we can, again, make the hydrogen initially by splitting methane and taking the carbon dioxide away and using the hydrogen. But as we gradually build more and more and more renewables, we can do more and more electrolysis to make that electrolysis of carbon-free hydrogen. Direct air capture, here's the plant in British Columbia Mark was alluding to. This uses gas to regenerate its solvent, so it contacts air, normal air, 420, 415 parts per million with potassium hydroxide. The carbon dioxide dissolves in the potassium hydroxide. That swaps over the carbon to calcium hydroxide, and that's heated to drive off the CO2. It's analogous to a paper making process. And that uses gas, methane gas, to heat that. And we're working with a company to bring that into Scotland, but instead of using methane gas, and I'm told actually that they do capture the carbon emissions from the methane combustion here at this plant. I haven't been personally to kick the tires, but that's what I'm told. But in Scotland, we'll try and use that heat regenerating step by using wind power, so we can have net carbon extraction from the atmosphere. I think, and oil companies can be our friends. Last slide. This is what needs to happen so that oil companies produce carbon. What we need to do is give a certificate to each ton of carbon. And with that certificate comes an obligation for that oil company to store the ton of carbon. So they sell us the energy, we use the energy, you and me and other people in industry use the energy. We pay slightly more for that energy because we're then paying for the oil company to put that carbon back underground. And as that carbon's put back underground, they're awarded a certificate which cancels the obligation. So we have to make oil companies join that up and make that a circular carbon economy. Whereas at the moment, the oil companies are basically cheating by producing oil, selling us the oil and the carbon, and then walking away from their obligation and liability to clean up the consequences of their product. So it's exactly analogous to the tobacco industry in the past, who refused to accept liability for the tobacco. So we will end up paying perhaps 5 or 10% more for our fossil fuel input to our industrial processes. So it'll mean paying a few percent more, less percent for the products. And that payment, small extra payment, will pay the oil company to dispose of the CO2. So what I've said is decarbonisation is urgent. I'm a big fan of all techniques which are decarbonising, whether it's efficiency, fuel switching, or carbon capture and storage, or recapture of the already emitted. So there should be a lot of common territory. It should be a way of trying to not have a bun fight about who's better than who, but it's really about how we can get as far on and as fast as possible and as cheaply as possible, even if some methods cost more than others. That's it.
Thank you. Right,